All right, so last day, we've already learned all the content from what we need to do. What we're going to cover now is just putting it all together in the different AP kinds of problems. Before we start this, tomorrow's quiz, it's a group quiz, and it's literally just AP problems. So there are going to be problems like this and problems that are similar to what's in your review. The review packet online is like 10 AP problems starting from 1984 and beyond. So tonight, in preparation for that group quiz, you need to work a few of those to get used to this whole putting everything from the thermo unit and the thermodynamic unit we're in now together. It's grabbing stuff from everywhere. So be sure to work some of those problems before tomorrow. It's popsicle sticks, so you don't know who you're going to end up with, and you can't depend that the person in the group is going to be smarter than you and you're going to work off of them. You don't know who you're going to get. So assume you have to work those by yourselves and prepare accordingly, okay? All right, let's do this problem. Now we're just taking it all and shoving it all together, all our knowledge. So the first question here says, consider the following reaction. It's water plus Cl2O gives you 2 Hochels, HOCls. And then they tell us the K, the equilibrium constant at 298 is 0.09. Take a look at the information they're giving. This is really important for you to pay attention to what information you have and don't have. So for Cl2O, you have delta G, H, and S. It's as if you're looking at the big data table. You've got everything from your Cl2O. For water, you only have your heat of formation and your S, so you don't have the delta G for water. Find delta G of the reaction, meaning delta G of this whole thing, using only information from above. Okay, you can't sit there and all of a sudden decide to open up a big table and try to answer this question. You only can use what they've given you. So hopefully you watched yesterday's lecture, and hopefully you'll be able to answer this question. How are we going to find delta G? Negative rat link. That is correct. How many of you watched the lecture? Okay. As of yesterday morning, there were only 20-something hits. So I hope you're not lying to me. Okay. Good. All right. Well, we'll see. I'll go check. I wish I could identify who watched it. That'd be awesome. No, I don't want y'all to comment on the video. Thanks. Negative. I know you can't comment because I took those away because I was getting people from China saying you're wrong, and I did not feel like dealing with it. Negative RT, LN, okay. All right. The little rats are up there with their tails linked. That's negative rat link. So we're going to calculate the delta G. What is our R? I guess I'll put the 4 in there because we did last period. On the AP equation sheet, it just says 8.31. When you get to the AP, only use what's on the sheet, okay? Because that's how they're going to round the answers. Not that you get it wrong, but why get it different at all? Now, what is the temperature we're going to use? How do you know that? No, because, bam, 298. So that K is only good at 298. So let's go ahead and solve. Last period, I want you guys to double check again. It's first period. 5970 is what they got. Yay. Joules per mole is the answer they got. I want to talk a little bit about, does this answer make sense? According to this G, is this a thermodynamically favorable or spontaneous reaction? No. Well, okay, let's look at the K. What's the magnitude of our K? K is less than 1. Which direction is that favored? The reverse. The reactants are favored. So because it's reverse, it means it's not favored in the forward directions, which means it's not thermodynamically favorable, so the delta G should be positive. So that kind of makes sense, okay? All right, so the next problem, I'm going to go ahead and write the equation down one more time just because once I move the thing up, I always have a hard time seeing it. All right, so use bond energy values, and you don't have it, but if you ever needed bond energies again, because we did this at one time or another, you'll get a table that looks something like this. Do y'all remember that? Okay. How did we use bond energy values to find delta H's, though? Who remembers? It was a very specific thing we did. Bonds. Oh. No. Bonds broken minus formed. You need to get that back in your head. And it needs to stay in your head until the AP. Bonds broken minus bonds formed. So that's what we're going to use. So let's go ahead and figure out what bonds we're breaking and what bonds we're forming, and then we'll look up the values if we need to. And again, you're going to be given a bond energy table. So we are breaking bonds there. What bonds are we breaking in water? 2 H's. Good. And what are we breaking in the other one? 2 CLOs. Nice. That's fine. You can say it whatever order you want. That's bonds broken. Minus. Look what we're forming. Bonds formed. And? What does that mean? Yep, 0. Delta H equals 0. We're breaking and reforming the same bonds. So delta H of our whole reaction, this is delta H of the reaction, is 0. Joules or kilojoules? Doesn't really matter. We'll just say joules. It doesn't matter. Either one. 0 is 0. Whatever. We good? If this wasn't 0, we'd take these, add up the bonds broken, and it's the sum of the bonds broken minus the sum of the bonds formed. Okay? All right. Find delta S of the reaction. Now what do? I don't have enough delta S pieces of information to find delta S because I don't have anything about this guy, and I have only the delta S of this side. So how can I find delta S of the reaction? Ghetto homies. Using what? We have the delta G. We just calculated that from RatLink, and we have the delta H because we calculated that from bond energy. So we're going to use ghetto homies. All right. So my delta G, which I already calculated, was 5970 joules per mole, is equal to 0 joules per mole minus, what temperature were we at with the K and all that business? 298. And then our delta S is what we're solving for. All right, so in joules per mole Kelvin, what? That's what they got, negative 20.0 joules per mole K. Is everybody good? In the hood. In the ghetto homie hood. All right. Now, you got to really look at what they're saying. They want you to find delta H of formation and the S just for this little guy. I'm going to give you a hint, and I'm going to tell you that this is going to be 2 separate calculations. Big mama for each of them. And what do we plug in for HOCl? Huh? X. Exactly. We know delta F of the whole reaction. We know delta S of the whole reaction. We don't know that little bitty piece of Hochul, of this guy. We don't know him. But we've got that information for H and S. We have the information of the whole thing. We just don't know him. So he's going to be our unknown, and we're going to solve. All right? So let's do delta H first, because that's easy to remember. 0 was our H of the reaction, is equal to products. It was 2 Hochuls, right? So that's our unknown, minus, I got to go back now, I don't remember, 1 times, I'm doing water first, 1 times negative 242 kilojoules plus, and then I think there's 1 Cl2O, and that is 80.3. Go ahead and solve for X, and let's see if your answer matches what they got in first period. They got 80.9. Okay. 80.9 kilojoules. Watch those units. That is huge, guys. Watch them, watch them, watch them. Are we good with the positives? All right. Are we sure? So it's negative or positive? Wow. Last period messed that up. All right. Wow. Go first period. All right. S. We're going to do Big Mama again, but we're going to set S equal to negative 20. Was that S? Again, 2 times X minus, I'm afraid to do this problem now because I'm afraid they're going to mess it up again. Go back. Water's S is 189, and the other one is 266.1. And these are joules per mole K. So your X will be in joules per mole K. That poor calculator. I feel as bad for that as I do for Chris's iPad. What did we get? And now it's in prison. What? 218. Can I get a second on that? And that's the appropriate sign? All right. Last thing then. How do I find K at 300 now? Plug it into RATLink using my other G. Delta G is equal to no, we have a K. We should probably find delta G how first. How, though? What are we looking for? Delta G at what? 300, and that's what we need to do. So what we need to do here is, using these two things above, find delta G at 300. So let's convert to, since we have to use RATLink, which is going to use joules anyway, let's convert both of these to joules. This is negative 80,900 joules minus 300 times my delta S of 218. I'm just taking the numbers from above, joules per mole K, and that's going to give me delta G at 300. Which is what? I think this is going to be wrong. 15,000? Can I get a second on that? Okay, I'm hearing a bunch of 14s. Negative 1460.00? All right, are we good with that? All right, so now what do we do to find K? Negative RATLink. Put in 300 and solve for K. I'm going to write these answers on the board. So negative 14. So what do y'all get? Remember, it's this divided by that, and then e to the answer. Whoa. Is that right? Sorry, people at home. Okay, first off, make sure you're doing e to the and not 10 to the. Well, 2.98, 25. Okay, so we're all kind of saying the same thing. All right, so let's see. Does that make sense as we increase the temperature? Well, it's not exo or endothermic, so we can't use it that way. I'm just trying to see if this number makes sense. We went up a lot, right? So we forced that reaction forward a lot. Is this what everyone's getting? All right, so we're going to go with it. K is equal to 2.98 times 10 to the 25th. All right, that's that problem. We good? Now, are you ready for the confusing one? All right. Before we do it, there's a couple things I want you to adapt. On the second page, I want you to calculate delta S just for the combustion. Take out that phrase and that phrase, because this is giving us double work of the same thing, so I think we only have to need to do it once. And that phrase. Calculate delta S for the combustion. Calculate delta G for the combustion is the combustion. All right, so that's how we're going to approach this problem. So let's go back. This is, again, is going to be a big time review from our original thermochemistry unit. Definitions. Write the balanced chemical equation that describes the combustion of 1 mole of oxalic acid. That's what we need to do first. Notice in the problem, they told us that the heat of combustion of oxalic acid is that. So when we combust oxalic acid, how much oxalic acid if it's heat of combustion? 1 mole. When we combust 1 mole of oxalic acid, that's how much heat is associated with it. And then they went ahead and gave us all those values of H and S. Notice the H of oxalic acid's missing because they're jerks, trying to make our lives hard. All right, so write the balanced chemical equation that describes the combustion of 1 mole. I'm going to combust 1 mole of oxalic acid. How do I do that? Good. We add it and we get CO2 plus H2O. Because I'm combusting 1 mole, by definition, I have to leave a 1 in front of it. So I'm going to balance it, and if that leads to fractional coefficients, so be it. I do my oxygens last. I have 2 carbons, 2 hydrogens. I have 5 oxygens on the right, but 6 on the left. Any ideas? Exactly. You make this a half. And that is the combustion. What I need you to realize here, and this is the part that makes the problem doable. If you miss this, you're going to panic and you're not going to be able to figure it out. This is the enthalpy of combustion. So this is the delta H that's associated with this whole reaction. Do you understand that? That is crucial to get that connection. All right, now once we know that, we can easily solve for different things associated with the combustion of that reaction. Part B is just another definition. Write the balanced chemical equation that describes the standard formation of oxalic acid. How do we write a formation equation? We form what from what? We form what? 1 mole of the substance. So in this case, it's oxalic acid. From its what, Grant? I heard you say it. No. Elements. From its elements. Was it Larson that said? Okay, whatever. You guys are in the same spot. I can't tell the difference. You look alike. All you white people look alike. All right. I'm white, by the way. All right, so here I'm going to form from the elements. What do I write? 2 C's, 2 O2s. All right, so that is by definition a formation equation. What number on this table is associated with this? Or what number that's not on this table is associated with this? Do you see delta HF? This little thing that I circled would be what that is. Okay? But we don't have it. So now, using the information given, calculate the heat of formation of oxalic acid. We want the delta H associated with this. We can't use that equation. We don't have anything. We don't have anything to plug into Big Mama or anything. But I can use the first equation. How am I going to use that to solve for formation of oxalic acid? Big Mama, and I know that Big Mama is going to be equal to what in this equation? That 246.05. That's the combustion is equal to, and I got to do the combustion equation. Don't try to set up anything other than, don't do that with the formation equation. It has to be with the combustion equation. 1 times, do we know this? Oops, nope, see, there we go. I went ahead and almost did it. We're going to do this, so 2 times CO2's delta H in the chart is 393.5 plus 1 times H2O, negative 285.8, products minus 1 times X, and then we know all the free elements have a delta H of 0. Does everyone understand how I set it up? Using the combustion equation, what do we get for our heat of formation of oxalic acid? No, not necessarily. What is it? Let's see. Oh, wow, they got 255 kilojoules per mole. Okay, tell me again. Are you kidding me? No, I'm just saying, I can't believe they messed up again last period. Let's double check what we're doing here. We're going to use 246.05, and we're going to set it equal to 2 times negative 393 minus that, products minus 1 times X plus, that's right. Wow. I can't believe, oy vey. All right. Negative 131.9 kilojoules per mole. Are we sure? God, y'all, I'm stressed out now. How can they miss it that much? I don't know. That's debatable. Okay, are we good? Moving on. Now calculate delta S of formation for the combustion of 1 mole of oxalic acid. So what I'm looking for now is the delta S of this whole reaction. How do I do that? Big Mama, and what do I use? All of these delta S's. And they give us everything we need in that list. So all we have to do is do Big Mama with those numbers. Okay, so now we're going to have to jump back and forth again. So we get, wrong way. So we get delta S of the reaction for the combustion is equal to, I wish y'all would read it to me. Can y'all read it to me so I have to make people seasick at home? So let's do CO2. Is that a coefficient of 1 or 2? 213.6 plus 1 times products minus 1 times X plus a half times. All right, what is our delta S? They got 275. What did y'all get? Oh, no, not 1 times X. Sorry, my bad. We know that. 125? Okay, now solve. My bad, my bad, my bad. a lot easier when all of this is on the same page. Oh, thank goodness I got something right. 275 joules per mole K. Okay? All right, calculate delta G then for the combustion. So now we're going to try to find the delta G of that same combustion reaction. I don't have any delta G's to do Big Mama from, so what do? Ghetto homies. So delta G is equal to delta H minus T delta S. Delta G is, you guys got for your delta H, I'm going to convert that to joules, negative 1319,000. Is that correct? Minus, it's got a little standard-y thing there. It's what I use for temperature. 298, and then delta S is 275 joules per mole K. And you're definitely going to get something different than these guys got because they used a different H. So I need multiple answers, please. Can we do, that's what I like scientific notation for. So, negative 1.4 what? And I need another sig. To the positive 6 joules per mole. Is this reaction spontaneous? Why? Yes, because the delta G is negative. Okay, and that makes me feel better because I did feel uneasy last period. They said it wasn't because they got a positive delta G, but combustion of something like this is usually pretty gosh darn thermodynamically favored. So yes, because delta G is negative. Okay, are we good? We're done.